I'm Todd, and this is my video presentation to my individual extension report. So I was in the percolation group, and in my individual extension report, I looked at directional percolation, namely gradient and invasion percolation. So in the group project, we looked at fairly abstract topics here in percolation, and I wanted to look at to the real world and use Python to create simulations and models to look at a real physical system like the movement of water in porous rocks. So this is a macroscopic view of a rock, and you can see there's many pores there, which can be equated to sites in our two-dimensional lattice percolation models. And looking at a microscopic view, we can see that the same holds true with many pores or sites that we can use our site percolation models for. Looking at the methodology, I first started looking at a constant gradient function to imply a gradient, a percolation gradient over lattices, and then looked at measuring statistics from this and exploring what they meant. And then relating it more to the real world, I looked at invasion percolation, which is more accurate but more involved, and it builds on the first model already created, where each site has its own individual threshold or effective threshold for percolation. So looking at the constant percolation gradient, we have this simple rule here where we can then vary A and G and measure characteristics as we change these parameters. Looking at a equals a half and different values of g, so 0, a half, and 1 respectively, we can see how this creates graphs with a clear gradient of percolation occupation probability. So looking at near the critical script, so a tolerance of 0.1, we can see characteristics that we'd expect to see with homogeneous percolation systems in 2 dimensions. This is a log-log graph, so it appears to follow a power rule because there's mostly a straight line. However, there clearly turns upwards towards the start and the end, and this is due to finite size effects of the lattice. We're only in a small strip, the critical strip, so it's not perfectly homogeneous, and we only have a fairly small lattice, so 200 by 200 and 500 runs to collect data over. However, it would be great to visualize this with a much bigger graph, but due to computing time and computing power restraints, we can't do this super effectively. Looking at then percolation fronts and a few definitions, this is very useful later on. And we look at then looking at the front width, so that's the standard deviation of hx, and we can see that it decreases, maybe not perfectly linearly, but definitely a negative relationship with gradient strength. Again, the fact it's not perfectly linear could be due to finite size effects. However, we can clearly see that as the gradient strength increases, the front width, so the standard deviation, decreases, which means that as gradient increases, the front gets squished down more, it becomes smoother and a much sharper gradient transition between states. So then looking at section 2, I looked at invasion percolation, where each site has its own independent effective threshold. So we have T of X and Y, which is modeled by uniform distribution, so a random number from 0 to 1, which is a capillary entry threshold, and then the gravity term at negative gy, which means that the sites lower down, y equals 0 being the top, are then easier to invade, and especially easier to invade as g increases. So then the randomness of T of X, because it is T of X and Y, is modeled by a uniform distribution that could cause them variance. So I used a fixed state seed to make sure it could be reproducible, and I could then do many different methods of percolation over the exact same background. And that's how I used a generator object to achieve this. The algorithm I used was to look at the percolation fronts, that's all sites that have been invaded, identify all the sites that then border the invaded sites, and then work out the effective threshold and pick the site with the lowest effective threshold to invade. And this creates these results. So looking at the graphs, we can clearly see that with a higher G, there is a much greater range of gradients. And we can see that as G is 0, there is no bias really. It's all due to randomness in the term, the effective threshold formula. We have T of X and Y, take away GY. With G equals 0, it's just based on complete background randomness, so there really is no bias. But as G increases, you can see channels form down the dominant path of least resistance. And as G does get larger, the channel gets much narrower. This is a slightly different way of starting. Instead of having the entire y equals 0 row begin invaded, we just have the center one site being invaded, which is at 25, 0. Similar pattern is still seen with a larger G creating a narrower cluster, but the percolation front is no longer horizontally spanning. as you can see from the graphs. So looking at the results, there is identical shapes in the G equals 0.6 between the universal front and the single front site starting off invaded. But however, in the G equals 2 case, the single invasion front does not fall into the same channel that the universal front finds. So the graphs look very, very different. So looking at extensions, we could find the universal lowest cost path using graphical methods, and we could see how often our algorithm finds it. Or we could then use pathfinding algorithms to find the shortest path that water would take, or the actual path water would take, and look at the water capacity of rocks relating to this. So a lot of content was covered in our very narrow area. I think we've very much explored these models in this. However, you'd need more complex models for relating it more to the real world. And for further analysis, more complex models with more variables would need to be taken into account.